Hey Scholarship Kiddies, and welcome to Lesson 6. We're continuing on with our redox topic and back titration. So let's just jump on in. So the first question we're looking at today is from the 2007 exam, and it's question 5A. Glycerine is a mixture of glycerol and water. Weighing 100 milligrams was treated with 50 ml of 0.0837 Ce4 plus solution and 4 moles of HCl at 60 degrees for 15 minutes. The excess for Ce4 plus solution needed 12 ml of 0.0448 moles per litre of Fe2 plus to reach the end point. The unbalanced equations are given here. So they've got glycerol to methanoic acid, Ce4 plus to Ce2 plus, and Fe2 plus to Fe3 plus. Calculate the percentage of glycerol in the glycerine sample. Okay, and discuss why back titration is used and compare the errors introduced in a back titration with a direct titration. So what's actually happening in this titration? So first of all, you've got the glycerol reacting with Ce4 plus. Okay, now if it's reacting with Ce4 plus and they've given these equations, then it's forming Ce2 plus. So the Ce4 plus must be getting reduced. 4 plus to 2 plus decrease in oxidation number, which means that the glycerol must be getting oxidized. Okay. It then says the excess Ce4 plus needed the rest of the Fe2 plus. Needed this amount of Fe2 plus. So the Fe2 plus is getting oxidized and the Ce4 plus again is getting reduced. Okay, so it's the excess Ce4 plus which is getting reduced from this total amount given at the beginning. Okay, so let's get going with the calculation. So the first thing we can do is work out the amount of moles of Ce4 plus that was totally added, so the total amount by C times V, and we get this amount of moles. The next thing that we can do is work out the number of moles of Fe2 plus from the final titration, that last step, and the Fe2 plus here is the Fe2 plus that reacted with the excess Ce4 plus. So C times V gives us this many moles of Fe2 plus. So we now need to find out, well, how many moles of Ce4 plus reacted then. So we do our balanced equations and it's a 1 to 2. Okay, so for every 1 Ce4 plus 2 Fe2 plus reacted. So we've got the number of moles for Fe2 plus, so we've got to half it to work out the number of moles of Ce4 plus. So half that number of moles gives us this many moles of Ce4 plus. Now this is that excess amount of Ce4 plus. So at the moment we've got our total amount of Ce4 plus and we've got the amount of Ce4 plus that was left over after the reaction with glycerine. So now we can actually subtract this number off this number to work out how much Ce4 plus reacted with the glycerol. And so that's what I've done here. Total minus the excess amount, and we're left with this many numbers of moles. Okay, so this is the amount of moles of Ce4 plus that reacted with the glycerol. We then need to do balanced equations, which I'm just hoping you guys can do. You'll just need to go through how to do that, just the normal procedure. Let me know if you don't understand. And here's the half equation for the Ce4 plus. So we need to balance that out. You've got 8 electrons and 2, so we need to times this bottom one by 4. And you can see here this is 1 glycerol to 4 Ce4 plus. And we've got the amount of moles of Ce4 plus. So therefore, to work out the number of moles of glycerol, we have to divide it by 4 because it's a 1 to 4 ratio. So once we've done that, the number of moles of glycerol is this. Once we've got a number of moles, we can then work out a mass. So we can do N times M, and they gave you the molar mass. So we times these two together, and you end up with 0.0901 grams. If you times that by 1,000, that'll just give you the answer in milligrams there. Now, the reason why we've put it in milligrams is in the question it said how much, they said that they'd added 100 milligrams. So therefore, if we do 90.1 divided by 100, that'll tell us the percent of glycerol in that glycerine mixture. And therefore, the percent of glycerol was 90.1. So that's quite a stock standard back titration question. I hope that made sense. The second part of the question as to why back titration was used. So titrations need to be really quick. And the reason why titrations need to be very quick is a lot of our reactants can then react with oxygen in the air and so forth. And so if you leave things for a long time, then you actually are getting incorrect results. So therefore, the reason why we did a back titration is because if you read the steps, the glycerol and the Ce4 plus needed to be heated for 15 minutes. So that's too slow for a direct titration to be used, okay? Far too slow just to expect that to be able to get accurate results. And so therefore the titration between these two is a lot faster and a lot more suitable. With a back titration, there is extra error because you have to take 2 measurements from the 2 titrations. However, it's far more accurate this way, and so we tend to think that back titrations are actually overall a much better idea. Hopefully that makes sense. So this question here is a bit of a hefty one, and you guys will need to probably bring this up on your screen as well, but we're going to spend the rest of this video going through this 2014 exam question too. This question's all on bleach, and we do bleach as an actual titration together, so when we will do that, who knows, whenever we're back together, but we will do it. So sodium hypochlorite is used on a large scale for water disinfection, including water and swimming pools. It's also the active ingredient in household bleach. So hypochlorite is OCl minus, by the way, and you do need to know that. So in the water purification industry, percent available chlorine is a unit of concentration used for hypochlorite use bleaches. 1 gram of a 100% available chlorine bleach has the same bleaching power as 1 gram of chlorine. The term available chlorine is used because most commercial bleaches contain substantial amounts of chloride ions which have no bleaching properties. A bottle of household bleach contains the following information. Active ingredient sodium hypochlorite, there's 42 grams per litre, and the amount of available chlorine, so remember the available chlorine up here, is 4%. Okay. Available chlorine when it's past its used by date is when it's 2% or less. The following procedure is carried out to determine the extent of decomposition of contents of the bottles of household bleach described above. A 20 ml sample of bleach is diluted to 250 ml using a volumetric flask. Okay? A 10 ml sample of this diluted bleach is reacted with excess potassium iodide along with 10 ml of sulfuric acid. And so what's happening here is the bleach in that 10 ml sample of diluted bleach, that's the OCl minus, is reacted with excess iodide, and iodine is produced. We then do a titration with good old thiosulfate that we know really well with a starch indicator because it's got a beautiful color change. So we use the iodine, react it with thiosulfate. Okay, here are the thiosulfate results. And the question is, determine the extent of decomposition of the bleach by comparing the available chlorine in the bottle with that on the label. Okay, team, so we're just going to go through. The key thing here is don't get fooled. They try to give you different values here. So 20 mils is diluted to 250. That's the dilution factor. But the actual sample we're analysing is 10 mils. Okay, and this here. So let's just move to the next slide. So here are the equations that were given to you. Here were the titer volumes, and I've just worked out, I've done final minus initial, and here are the values, and I've done an average titer. I've not included this value because it's outside the concordancy. The rest are all pretty close, and that one seems quite far out from the rest, so I've ignored that value and kept the other ones, which are within 0.2 of each other. I've then calculated the number of moles of thiosulfate using the concentration and my average that I've just done, ensuring that I convert to litres, of course. And here's the number of moles of thiosulfate. So this is the amount of thiosulfate used in that final step of the titration. Now what we can actually do here is you can see that 1 OCl minus produces 1 iodine, and 1 iodine reacts with 2 thiosulfate. So if we just want to compare these two, it's a 1:2 ratio. So it's 1 OCl minus for every 2 thiosulfate. So therefore we've got the number of moles of thiosulfate. So therefore we can actually just divide it by 2 to get the number of moles of OCl minus. because remember, you cover up the one you're looking for, and so that has to be timesed out up here. And so this is the number of moles of OCl minus. So from there, if we've got the number of moles, we can convert that number of moles to a concentration. Now remember, our volume was 10 mils, so N divided by V, that's our concentration of our diluted bleach. Now from here, we need to work out, well, what's the concentration of the undiluted bleach? They had taken 20 mils of undiluted bleach and diluted it to 250, and that's what our 10 mils was taken from. So we need to work, that's our dilution factor, and we times that by the concentration of our diluted bleach, and this is our concentration of our bleach in moles per litre. Now, commercial products are always listed as grams per litre because most people don't understand what the hell a mole is. And so we need to convert that moles per litre into a grams per litre. And we easily do that by timesing by the molar mass. And you'll see why, because this unit here is moles divided by litre, and this unit, the unit for molar mass, is grams per mole. So if you times these together, you end up cancelling out the moles, and you end up with grams per litre. So that's how that comes about, just so you know. So we need to work out, first of all, the molar mass of NaOCl, and so we add all of those from the masses on the periodic table, and then we take our concentration in moles per litre, times it by the molar mass, and you end up with this being your concentration, 35.45 grams per litre. Now, in the question, they said that if you had 42 grams per litre of bleach, the maximum amount of available chlorine was 4%. So 4% is your maximum amount. So we need to see how much we've got. So I find this to be the easiest technique. I first of all worked out, well, what is the percent of the chlorine that I've actually got in there using this concentration. So 35 divided by what should be there, and there's actually 84.4% chlorine. Now we know that if it was a full amount, only 4% of it would be active. So I'm going to then work out, well, what percent have I got if I've got 84.4? So I times that by 4 over 100, and it turns out that the amount we've got is 3.38. This is another method here. If that works better in your head, please do that. This just works so much better for me, and I process this way. I didn't work it out this way. So if we've got 3.38, that's well above the 2% that it's deemed off the bad use by date. So therefore we're all good. Okay, this bleach is still okay, and we can work out how much of it dissociated, because if we've got 84.4%, and if this was 100%, then you just subtract it off. So 100 minus 84.4, so 15.6 of it dissociated, which is pretty cool. Yeah, so I hope that makes sense. Any questions, let me know. The next part of the question is, it says the decomposition of bleach is a disproportionation reaction where an atom in a particular oxidation state connects both the oxidant and reductant. Use the following to explain why the hypochlorite ion decomposes. So this is really cool, because I love how this question actually starts with a real life example and then says to you, well, this is why it happens. It's super cool. So we know disproportionate's when the same species gets oxidized and reduced. So the only species that's common to both these half equations is ClO minus. So ClO minus must get oxidized and reduced. So if it gets oxidized, it produces this. If it gets reduced, it produces Cl minus, and you have to do your half equations. Let me know if you have any issues with those. We have to times the second one by 2 to balance out the equations, and this becomes our full equation here. So you always have to produce a full equation when you calculate a cell potential to get full marks in scholarship. We then do reduction minus oxidation to produce a cell potential, and we can see that this value is positive, which means that the reaction is spontaneous. So that means that ClO minus will disproportionate, and so therefore the reaction will occur, and that's how come the amount of chloride decreases over time, because it naturally reacts with itself, which is pretty crazy. So hopefully that has made sense. I'll be back soon for part B of Scholarship Lesson 6.